Hello, Internet. Since I know that nobody, and I really mean nobody, will watch this video on topological graph neural networks, I can be completely honest with you today. Because you know what? It is raining, it is freezing cold. We are in another lockdown for some global pandemic, and I guess you know what I'm talking about. And therefore, I decided to have a look at the topological graph neural network research and development activities. And I found this conference paper here for ICLR 2022. And if you think that you know something about topological GNNs, welcome. Let's have a look at this together. Now, those scientists, they're from Switzerland, Belgium, Germany, so a European consortium. They propose a novel layer that incorporates global topological information of the graph using persistent homology, you know, these famous diagrams. And they want to achieve more expressivity than message passing GNN. And of course, in relation to the Weisfeiler-Lehmann graph isomorphism test, the WL1 test. I showed you the W1 test in my last video. And they say that augmenting GNN with their methodology leads to an improved predictive performance for a graph classification and node classification task based on the graph isomorphism problem. So this sounds interesting. How they do this? Let's start. Of course, we have GNN based on iterative message passing scheme. Yes, we know this. We have information collection over the neighborhood of every node. And of course, they cannot capture some topological structures in graphs, such as cycles. Yes, we know this. So they say, hey, we add another layer, and this layer is specific that it will learn and increase the expressivity in graph learning tasks. This is great. Let's have a look at this. And of course, we start at computational topology because we want to be able to compute this with our GNN algorithms. And the nice thing here is they did it in a form that it is really a layer you can insert into your GCN, into your Graph Convolutional Network. I don't know, you're going to have 4 or 5 traditional layers. And if you substitute one of the GCN layers with this topological layer, you should be able to get some additional information about the global structure of your graph objects, which is gorgeous. And you know, graphs are also topological objects. Therefore, computational topology now added to our classical GNN methodologies. What we need to know, we have the Betty numbers. You know, the number of connected components is here beta 0, and the number of cycles is, as always, classical beta 1. And they're also known as the 0-dimensional and 1-dimensional Betty numbers. And of course, they are invariant under graph isomorphism to be computed efficiently. And then what we have here is graph filtration. Now, there's one term I want you to really have a close look at, and this is graph filtration. It is a sequence of nested subgraphs of our graph. And a filtration or graph filtration makes it possible to obtain more insight into the graph by monitoring topological features of each particular GI. And calculate their topological relevance, also what we know as persistence. And you know the persistence diagram, we don't have to talk about this, this is the classical diagram, and we enter here the persistence homology area. And of course, the use of the filtration function with d equal 1, so we limit ourselves to d equal 1, we accentuate certain structural feature of a graph. Now, if you say, okay, so it is all about filtration, well, not really, but the appropriate filtration function f is really crucial for our undertaking. So, related work, I also showed you the graph kernel methods in one of my last videos. And of course, Graph Neural Network with the work on XU. And the persistent homology, we just talked about this. The core is the notation of filtration. This is a sequence of nested subgraphs or simplicial complexes in a higher dimensional settings. And this is significant of importance to learn one task-specific filtration function. And in the end of this video, I will show you an example, a very simple example of how those filtration functions work and how you can imagine them visually. Maybe this will increase your understanding if you are not the pure mathematical formula guy or girl. So here we go. The idea is that we have to learn multiple filtrations of a graph in an end-to-end manner. I will show you in a second how the authors propose to do this. We have now the main part. Here is the topological graph layer. They describe this a set of d-dimensional node attribute vectors, and then we have a family of k-vertex filtration functions. But there is a very simple, nice picture that shows you the different steps. And let me focus on the different steps. And if you want to read the mathematical structure of each step, you are welcome. I'll leave you the link to this paper, of course, in the description of this video. So we start with our node features XV we have from our graph. And then what they introduce is what they call a node map. And this node map, as they say here, node map maps our node attributes to k node values. And then what they get is they get k different views of the graph, or k different filtrations of our graph. Remember, these are not interactive and these are not interlinked. These are just different filtrations, a set of different filtrations of our graph G. And then you calculate, of course, the persistence diagram and the classical way we do this. And then the next step is something very nice, that is embedding functions. And this embedding function comes from another paper, and I will leave you the link to this other paper also in the description of this video, but there's some work going on to be able to understand where this function comes from, what this function does. But let's say we just aggregate all these embedding functions and we define a new output. And this new output that we get, let's call it x tilde, is then where we define our loss function, and then with some gradient descent we can go back right to letter A, to our node attributes, and have here gradient descent going back to the node attributes. So we have a loss function, we have a gradient descent, and this is more or less what we're going to do in our substituted convolutional layer. This is now a topological aware layer, if you want, within a GNN. So we can apply our classical GNN, I don't know, DGL methodology that you have, our model. And this is more or less the layer functionality explained in simple, easy terms. At least the way I understand it. So, a layer that can be integrated into arbitrary GNN. Yes, the details on the filtration computation, enjoy it if you want. Important is limitations. And this is something I said, wow, our approach is therefore limited to connected component and cycles only. So that they restrict themselves to L equal 1 here. Of course, multifiltration, the classical literature is Gunnar Carlsen, 2009. What a genius. Another genius, I think, working on this on a higher level structure where they're going higher than just cycles. Higher motifs is, I think, Professor Bernstein, but this would be the topic of another video. So the embedding function is a little bit explained here. Have a look at it. Yes, there is a theorem that proves you that we can have here a differentiability on this filtration, but just let's assume it is. There is a proof, there's a theorem, there's also a proof attached to this. If you love it, if you're mathematically really interested in this, have a deep dive, enjoy it. Otherwise, we can go on, and what they tell you Well, the Weisweiler-Lehmann test can distinguish certain parts, and they say, oh, a toggle can also distinguish all the graphs, WL1 can distinguish, and in addition, we can distinguish even more than W1, L1 can, and this is the whole idea why we have to extend this with the global topological information of the graph, because, you know, in the GNN, the message parsing classical POV formulation, we just have the local environment more or less focused. Persistent homology is at least as expressive as Weisweiler-Lehmann one-dimensional. Well, of course, there's a proof, beautiful. You look at the proof, you look at the setup. They have now a benchmark, and they say, hey, we have a graph convolutional network with 4 levels, with 4 layers, and then they build a GCN 3 with one global topology aware layer. This is the GCN 3 toggle 1. And I give you then all the performance data. You can have a look at this. No problem. I think one interesting part is they discuss here, if I understood the data correctly, that maybe a lot of information is hidden in the node attributes already, so that the global graph structure does not always provide you with some significant additional information, but that the node attributes already carry a lot of the information. So somehow, if you clean up for this effect of the node attributes dominance, you need to do this to really see the added benefit that you have for your specific task, for your specific graph, if you switch on this additional information on the topology of your graph to really get better results. Yes, you can have a look at this, yes, and what they do, they present a new methodology, a generally applicable layer that incorporates topological information to any GNN architecture. They have the dimensional compatibility, they have the same dimensionality, this is nice. And what it does, it learns filtration functions. And then this is it, more or less. It's nice, it's really nice to see a paper with a statement concerning the reproducibility, so that we can verify this, we can build it in the lab. But what I want to show you, and this is now the last part here, they have a very nice annex. And if you want to have a short deep dive, they really recommend to you this. They are focused on the topological data analysis, formal introduction to persistent homology, and the simplicial homology, algebraic topology. We have our 0 simplices, this is our vertices, and our 1 simplices, of course the edges. And yes, I done the homology group, the quotient group. We don't have to focus on this. The Betty numbers I already told you about. Common use complexity measure, yeah, they can be used to discriminate manifolds, beautiful. Persistent homology, we talked about this. Filtration, yeah, this is already, yeah, there's the group aspect, then the classical diagrams. And then, yeah, this is what I wanted to show you. A very easy explanation of graph filtration. Graph filtration, or learnable graph filtration, for me is one of the key parts of their methodology. And I think if we really want to have an understanding of the method, we have to understand how they want to learn the graph filtrations and what the different graph filtrations are based upon. And they give us here 2 examples, and this is really nice, and I want to show this to you for the last time. So we have here a graph. This is a very easy graph, and they tell you the filtration values are shown as the numbers next to a vertex. So here we have 1. Yeah, and they have degree-based filtration of the graph. So our numbers are the degrees of our vertices. So we have here 1, we have here 1, come on, here we go, so 1. Then we have here 2 ingoing, outgoing connections, and then we have here 2 nodes or two vertices. that we have a connection 1, 2, and 3. 1, 2, and 3. So this is now the filtration values as indicated next to the vertices, and then we use denote the filtration value at step J, blah, blah, blah. So in each filtration step, and you have the G1, the G2, and the G3, the next node and edges added to the graph are shown in red. So when we start, we have these two little nodes here. I cannot mask them, so you can see in G1 we have this with indicator 1. Of course, we are degree based, so we start here at 1. Then degree based is in G2. We have now our node with 2 edges. If you want, this is now in red. So we have 2 black, 1 red. And if we go then to our degree-based filtration notation, we have then G3, and then in red you can see the new part, and these are the 2 nodes that have, for example, 3 edges. And this is a very nice filtration, but it is a degree-based filtration. Now you can choose another filtration, but the nice thing here is that we get really quite fast, I would say. Let's follow the text. Since all edges are inserted at A3, we obtain the following persistence diagram. Yeah, okay, this is our persistence diagram, and then the single tuple form indicates that beta 0 is 1. There's only one cycle in the data set, which is created at A3. Leading to this, so if we change the filtration, and let's do another color, If we change the filtration, such that each vertex has a unique filtration value, and this is just a numerical value. So what we do is we just have 1, well, boring, 2, in any order, 3, 4, and 5. So you see we have now different integer attached to its vertex, and then we do more or less the same. We have our filtration, and G1, yes, of course, here the one indicated, G2 is then this one, but this is not such a nice, clear, fast insight providing filtration, I would say. As you can see, G2, G3, G4, G5, and another type of filtration. And as they said here, the connected components, the beta zeros are not created at once, but more gradually. Intra created a filtration 2, merges with another component near this leads to the topological from a younger component. Again, there's only a single cycle in the data set, which we detected at A5. So you can see this is, in my point of view, a faster, more elegant, but it is specific to your specific task. So choose your filtration very, very carefully. And it's nice, you see why we have here learnable filtration, filtration of simple graphs, and computational details. Should we go? No. Yeah, if you want to have the mathematical proof, there is a very nice proof. Have a look at this. Otherwise, I think we can trust the authors of this paper. Empirical expressivity, express setup, computational complexity. This could become interesting for us if you want to do the code. Yes, of course, not suggest to use persistent homology of arbitrary dimensions. Yes. Approximating. Yes, of course. Nevertheless, yes. Learning schedule rate. Yes, learning schedule rate. Compute resources. They had 8 GeForce GTX 1080. My goodness. A GTX 1080, they still exist. My goodness. Okay. An Intel cluster. This is great. Okay. Hyperparameters. This is nice. So really, if you want to have your own configuration, you know what their parameters and hyperparameters were that they used. Really, really nice. Molecular structure. Yeah, of course. You're interested in the chemical bioinformatical branch. So all in all, a very nice paper if you want to start to learn about, about topological graph neural networks. And up until now, you just had a GNN, a classical plain GNL. You programmed in the deep graph library on the PyTorch geometric library. Hey, welcome. There is a really nice add-on, an addition concerning the global topological structure of your graph, and a very nice work I wanted to show you. I hope you enjoyed it a little bit, and I see you in my next video.